We're given the separation between the plates as 1 millimeter, and we're told that a 12-volt battery is connected to the capacitor. So we have a 12 volt here. This means that the upper plate is at the same potential as the positive terminal of the battery, and the lower plate is at the same electric potential as the negative terminal of the battery. So this means that the upper plate is at a potential 12 volts higher than the lower plate. Now, so the potential difference across the capacitor is 12 volts. So we want to find first the electric field between the plates. The electric field between the plates of a capacitor is just the voltage difference, the potential difference, divided by the separation, the distance between the plates. This is 12 volts divided by the separation, which is 1 millimeter. That is 10 to the minus 3 meters. This is volts meter. So this means that it's 12 times 10 to the 3, 12,000 volts per meter. This is the electric field. The units are volts per meter. That's, in fact, equivalent to newtons per coulomb. Okay. Next, we want the surface charge density. This is the charge on the plate divided by the area of the plate. Now we know that the electric field, by the way, which is the electric field between the plates, is directed from positive to negative, and it's constant, and it has this magnitude, 12,000 volts per meter. We know that the electric field, E, between the plates of a parallel plate capacitor is just sigma over epsilon 0. So this means that sigma is epsilon 0 E. Epsilon 0 is 8.854 times 10 to the minus 12 in SI units, and E is 12 times 10 to the 3. So 12 times 8.8, this is about 105. 105 times 10 to the minus 9. So it's about approximately 105 times 10 to the minus 9, that is, it's 1.05 times 10 to the minus 7. And the units of sigma, it's a surface charge density, so it's coulombs per meter square. How about the capacitance? I'm given A, the area, and I'm given D, the separation. So the capacitance is right away epsilon 0 A over D. Epsilon 0 is 8.854 times 10 to the minus 12 in SI units. The area is 10 centimeters square. Now, the 1 centimeter is 0.01 meter, 1 over 100 of a meter. So that's 10 to the minus 2 meter. So the 1 centimeter square is 10 to the minus 2 meter square, which is, so this means that 1 centimeter square is 10 to the minus 4 meter square. So 10 centimeter square. So this is 10, and the centimeter square is 10 to the minus 4 meter square. That's epsilon 0 A over D. D is 1 millimeter, which is 10 to the minus 3 meter. So that's 10 times 10 to the minus 4 is 10 to the minus 3 divided by 10 to the minus 3. That's just 1. I don't need to put units here, since everything is in SI. As long as everything is in SI units, you don't need to include them here, but you just put them at the end, as long as you stick to SI units. So I'm left with 8.854 times 10 to the minus 12, and the units of the SI units of the capacitance is a farad. Now 10 to the minus 12 farad is what we call a picofarad. So this is 8.854 picofarad. Next, we want the charge on each plate. Now, since sigma is the charge on the plate divided by the area of the plate, this means that Q is sigma A. Sigma times the area. Sigma, the charge density, we have it here. 1.05 times 10 to the minus 7 coulombs per meter square. And the area is 10 centimeters square, so it's 10 times 10 to the minus 4 meter square. So we get 10 to the minus 11 times 10, that's 10 to the minus 10, so it's 1.05 times 10 to the minus 10 coulombs. This is Q. This is the charge on each plate. Of course, it's plus charge on the upper plate, so it's plus this, and it's negative. It's plus Q on the upper plate, in this case, the one connected to the positive terminal, and it's minus Q on the lower plate.